This is homework 3, and we will be doing problems 1, 3, 10, 12, 23, 32, 43, and 51. Problem 1. And by the way, this is from the book University Physics, 14th edition. Problem 1 reads, a squirrel has X and Y coordinates, 1.1 meter and 3.4 meters at one time. So X, Y equals 1.1 and 3.4 meters. At time t equals 0. T equals 0, X and Y. All right. At time t equals 3 seconds, X and Y equal 5.3 meters and negative 0.5 meters, respectively. For this time interval, find A, the components of the average velocity, and B, the magnitude and direction of the average velocity. Here we go. All right. So for the X component, the average X is going to equal X final, or X2 minus X1 over T2 minus T1. And V average Y is going to equal Y2 minus Y1 over T2 minus T1. So that's going to equal, let's see, 5.3 minus 1.1. That's meters. Mustn't forget our units. Over 3 seconds minus 0. We'll just put 3 seconds here. So this is going to be equal to 1.4. 1.4 meters per second. And in our y coordinates, we're going to have a negative 0.5 meters minus 3.4. And once again, that's the same time interval, 3 seconds. And that's going to give us a negative 1.3 meters per second. And now, are we converting to polar? I reckon we are. We've got to convert to polar. So let me clear up some board space here. We'll pause, clear up. All right, now to convert to polar, we're going to have V average equals the square root of V sub X average squared plus V sub Y average squared. And that's going to be equal to the square root of 1.4 meters per second quantity squared plus a negative 1.3 meters per second quantity squared. And that's going to give us 1.9 meters per second, the average. And then, of course, that's the magnitude. We need to find the direction. So that's going to be tan inverse of Y average over X average is going to give us theta. So that's going to be a tan inverse of negative 1.3 meters per second divided by 1.4 meters per second. And that's going to give us a negative 0.92. Oh, no, sorry. Let me erase that. I'm looking at the wrong thing. Okay, that's going to give us a negative 42.9. And that's going to be in the fourth quadrant. So we take 360 minus 42.9, which is going to be 317 roughly. 317. All right, that was number 1. Number 3 says, it's a calculus problem. A web page designer creates an animation in which a dot on the computer screen has position. All right, and the position is R equals 4 centimeters, 4.0 centimeters, plus 2.5 centimeters per second squared times t squared I, and that would be plus 5.0 centimeters per second times t j. J. Okay, so this is the whole I component, and that's the j component. And it goes, find the magnitude and direction of the dot's average velocity between t equals 0 and t equals 2. So A, we're going to find the magnitude and direction between t equals 0 and t equals 2 of the average velocity. And B, find the magnitude and direction of the instantaneous velocity at t equals 0 and t equals 1. So B is the instantaneous at t equals 0 and t equals 1 second. Oh, this is 2 seconds. And then find and show the velocities show the velocities calculated in part B. Oh wait, no. Sketch the dot's trajectory from t equals 0 to t equals 2 seconds. This is C. And show the velocities calculated in part B. So let me get some board space. All right, the average equals R2 minus R1 divided by T2 minus T1. All right, so we have at t equals 0, R, this is going to be 0, that's going to be 0, R equals 4 centimeters I, 4.0 centimeters I. At t equals 2 seconds, R is going to equal 14 centimeters I plus 10 centimeters J. All right. So let me see what I'm supposed to do here. Okay, so I'm finding the average velocity between those times. All right, so B average is going to be delta x. B average of x is going to be delta x divided by delta t, which is the I component. And V average of y is going to be delta y over delta t. All right, we're going to have, this guy is going to be 10 centimeters over 2 seconds. And this guy is going to be 10 centimeters over 2 seconds. So we're going to have 5 centimeters per second for each one. I need a little board space. Let's see, doing your, so 5 centimeters per second for each one. So now we have to convert to polar, and let's do that right here. The average equals square root of 5 centimeters per second squared plus 5 centimeters per second squared. That's going to be equal to 7.1 centimeters per second. And the direction, tan theta equals 5 centimeters per second over 5 centimeters per second. That's a tan of 45. That's going to be 45. Tan of theta equals 1 is at 45 degrees. So that's going to be 45 degrees. All right, so that is a 3A. Let me get myself some board space and I'll continue. All right, now for B, I'm supposed to get the instantaneous velocity at those two values. And so to get a pen, to get the instantaneous velocity is dr dt, v equals dr dt. And that's going to give me this guy, that the derivative, taking the derivative is 2 times 2.5 centimeters per second squared times t. That's I plus 5 centimeters per second j. All right. Now let's see, these two values 0. I'm going to have a v at t equals 0 is going to simply be 5 centimeters per second. And there's no I component, so the angle there is just going to be 90 degrees. There's only a j component. It's positive, so it's going up the y-axis, and so that angle is going to be 90 degrees. Now at t equals 2 seconds, v at t equals 2 seconds, I'm going to get, let's see, v sub x is going to be 10 centimeters per second, and v sub y is going to be 5 centimeters per second. And so to get my magnitude, I'll just take the 10 centimeters per second squared plus 5 centimeters per second squared, and it's going to be equal to 11. V is going to be 11 centimeters per second. And then let's see, to get theta, I'm going to, it's going to be what? 5 over 10. Tan inverse of 5 over 10 is going to give me 45 degrees, right? 45 degrees. All right. So that's B, 3B. All right, for the next part, sketching the trajectory, that's going to be the X and Y graph. Going to be what we see on the computer screen is going to be the X versus Y. So we have for t equals 0, and the slope is going to be the velocity. So we're going to use all those values we calculated. Let's see, 6, 8, 10, and calculate some more. 2, 4, 6, 8, 10, 12, 14. So at t equals 0, let's see. 0, x is going to be 4, y is going to be 0 right here. And our velocity is going to have a slope of 90 and have a value of 5 centimeters per second. So it's going to be looking like that. All right, at t equals 1, we are going to have, let's see, 4 plus 2.5 times 1 is going to be 6.5. So right about here. And y is going to be 5. So here and here. Wait, 5 is here. 6.5 is right about there. So we're going to have our velocity is going to be 7.1, and the angle is 45. So something like this. And finally, at t equals 2, we've got 2 squared times 2.5. Let's see, let's do that real quick. 4 times 2.5 is going to be what, 10? 2.5 times 4 plus 5 is going to be 15. We've got 15, so it's going to be right here. This is 2. And then y is going to be 10. So 2, 4, 6, 8, 10. So right about there. And we're going to get an angle of 27 and a magnitude of 11. So it's going to be something like that. This is V equals 11. This is V equals 7.1. And this is V equals 5. And we're going to have some kind of curve. These are our tangent lines, remember? Tangent lines. Yeah. Okay. So that's what the particle on the screen is going to look like. That's number 3. Okay, number 10 says a daring 510 Newton swimmer dives off a cliff with a running horizontal leap as shown in figure 310. What must her minimum speed be just as she leaves the top of the cliff so that she will miss the ledge at the bottom, which is 1.57 meters wide and 9 meters below the top of the cliff? So we've got this swimmer. She's got to clear 1.7 meters. And this guy is 9 meters. All right, this is a nice, and so we need to know what V naught has got to be. All righty, so we know that V sub x has got to be 1.7 meters per second over t. Whatever this t has got, takes her to fall there. She's got the x component has got to be 1.5 meters per second over t. All right, so I'm going to get my t. My time is always dictated by the y component, so I'm going to determine how long it takes me to fall 9 meters. So 9 meters, this is going to be my y component, v sub y, where I'm going to use that handy dandy polynomial x final equals x initial plus v naught t plus 1/2 at squared. I'm going to have x final is going to be 9 meters. And it's conventional to use this as a negative, so I'll go ahead and do that. Negative 9 meters. I'll call this 0. Equals 0 plus, she's got just leaps out in this x direction, so she doesn't have any downward velocity. So this is going to be, v naught is going to be 0. Plus a 1/2 times a negative 9.8 meters per second squared times t squared. So this is going to be, these are going to go, negative 9 meters times 2 divided by negative 9.8 meters per second squared equals t squared. Now I'm going to take the square root of both sides. And solving for t, I'm going to get 1.3 seconds. So now I know that I have to have at least 1.7 meters per second. 1.7 meters, sorry, 1.7 meters divided by 1.36 seconds. So she's got to be going at least, let's see, 1.29 meters per second. 1.29 meters per second. And that'd be really calling it close. So I'd bump it up a little higher than that. Anyway, that's calling it close. All right, so that was number 10. Number 12. Number 12 says a rookie quarterback throws a football with an initial upward velocity component of 12 meters per second. 12 meters per second. So this is going to be v sub y. And a horizontal velocity component of 20 meters per second. So v sub x is going to be equal to 20 meters per second. Ignore air resistance. How much time is required for the football to reach the highest point of the trajectory? So A, we want to know that. And B, how high is this point? So, all right, so B is how how high is this point, and C is how much time after it is thrown is required for the football to return to the original level. How does this compare with the time calculated in part A? How far is the football travel horizontally during this time? This is a typical projectile problem. All right. So I'm going to solve for the time. It's going to go something like that to get here. So I know that when it's there, my velocity in that y direction is going to be 0. So I'm going to use this v final equals v initial plus acceleration times time. All right. So it's going to be 0 meters per second equals 12 meters per second minus 9.8 meters per second squared times t. All right. So I'm going to subtract 9.8 meters per second for both sides. So I'm going to subtract 12 meters per second. So negative 12 meters per second equals negative 9.8 meters per second squared times t. I'm going to go ahead and divide through negative 12 meters per second divided by negative 9.8 meters per second equals t. Let me just go ahead and see what that is. T is going to be 2.45 seconds. Oh, wait a minute. No. Can't be that. It's going to be 1.22 seconds, right? A equals 1.22 seconds. All right. Now, what is the next challenge? Is to how high is this point? All right. So we're going to go x final equals x initial plus v naught t plus 1/2 at squared. We're going to solve for this guy. I'm going to once again use the y component. And he kicks it, so the x final equals 0 plus 12 meters per second times a 1.22 seconds plus a 1/2, and let me just do a little erasing, get myself some board space. All right. One-half times a negative 9.8 meters per second squared times 1.22 seconds squared. Anyway, we're going to have, let's see, x final is going to equal, let's see, what is B? 7.35 meters. So B equals 7.35 meters. All right. Now, what was the next question? How much time after it is thrown is required for the football to return to its original level? Well, this is a symmetric problem, so it's going to be twice this. So that's going to be 2.44 seconds. Anyway, finally, how far is the football traveled horizontally during this time? Okay, so that's going to be, how far is going to use v sub x equals, or x final equals x initial plus v naught t plus 1/2 at squared. Horizontally, we're going to use a horizontal component, so x final equals 0 plus 20 meters per second times 2.44 seconds. And there's no acceleration in that direction. So the answer there is going to be 49 meters. C equals 49 meters. And now I'm going to draw graphs. So let me give myself some space here. All right. Am I going to do that for each x and y component, or let's see. Draw x versus t, y versus t. Okay, x versus t, y versus t, x, t, and y. Okay, so v of xt All right, so yes, I'm going to do it by components. All right. All right, so if our x versus t, the position in the x direction, I've got a constant velocity. So my slope is going to be my velocity. It's going to be this, which is 20 meters per second. So this is 1 second, and that's 20 meters. This is 2 seconds, and this is 40 meters, and so on and so forth. That's pretty straightforward. And so now for my v sub x versus t, it's going to be a straight 20 meters per second. That's that. That's pretty straightforward. All right, for my y versus t, I'm going to go have a positive. It's got an acceleration, so it's going to look like this. Y versus t, it's going to go up and reach a maximum and then start going down. And what did we determine that maximum was? 7.35 meters, I believe. 7.35 meters. And that occurs at 1.22 seconds. And then for my v sub y versus t, it's going to start at 12 meters per second, and it's going to end at negative 12 meters per second. And it's going to just have a straight negative, the slope is going to equal to negative 9.8 meters per second squared. And there you go. That was number 12. Number 23 says, the Earth has a radius of 6,380 kilometers. R equals 6,380 kilometers. And turns around once on its axis in 24 hours. So T equals 24 hours. What is the radial acceleration of an object on the Earth's equator? Well, the radial or acentripetal or radial is going to equal to v squared over r. All right, so v squared, v is going to equal to the circumference divided by the time, the period. All right, so let's figure that out. This is going to be 2 pi r divided by 24 hours, and I don't like hours, so I'm going to be 3,600 seconds over 1 hour. All right. And let's see if I can get a real quick solution over that. No, let me just do this is v squared over r. I'll just go ahead and do it. V squared over r is going to equal to this thing squared divided by r. So 2 pi r over t, and this is all squared divided by r. So it's going to be 4 pi squared r over t squared, which is, let's see, 4 pi squared, r is 6,380 kilometers, divided by t squared is 24 hours times 3,600 seconds per 1 hour. And this guy down here is also squared. And the answer is going to be 0.34 meters per second squared. I'm sorry, 0.034 meters per second squared. That is the radial acceleration. Now, to convert that, wait a minute. Is that what I get? The 40? No, that's just, yeah, wait. 0.34 meters per second squared, right. Let me see here. Give your, okay, what is the radius object? Okay, give your answer in meters per second, a fraction of g. If a radial of the at the equator is greater than g, objects will fly off the Earth's surface into space. Okay, now to convert that into g's, we have 0.034 meters per second squared times 1g over 9.8 meters per second squared. So in g's, it's going to be 3.4 times 10 to the negative 3 g's, 10 to the negative 3 g's. All right, that was 23. I didn't solve the second part of 23. Okay, so the second part of 23 reads that if this acceleration is greater than g, things are going to fly off the Earth. So it wants us to determine the period for which things will start flying off the Earth. So in order to do that, we have a radial equals 4 pi squared r divided by t squared. So we're going to solve for this. So a radial, to set that up to equal to g, is going to be equals 9.8 meters per second squared. I'm going to do this. T squared equals 4 pi squared r divided by 9.8 meters per second squared. And take the square root of both sides. And if you do that and do all the calculations, you're going to get 5,070 seconds. And in order to convert that to hours, you're just going to go ahead and divide through by 3,600 seconds per 1 hour. And you're going to get 1.4 hours. So we would have to be spinning pretty quickly in order to fly off. All right, that was the second part of 23. Okay, problem 32 says, two piers A and B are located on a river. B is 1,500 meters downstream from A. Two friends must make round trips from pier A to pier B in return. One rows a boat at a constant speed of 4 kilometers per hour. So the rower is 4 km per hour. And the other walks on the shore at a constant speed of 4 kilometers per hour. The velocity of the river is 2.8. So V river, how about V boater? And this is 2.8 kilometers per hour. Okay. Let's see. How much the velocity of the velocity of the walker is 4 kilometers per hour. So the boater and the walker are going the same speed, but the boater has to fight the stream going upstream, and he gets a little bit pushed going downstream. So let's see, we've got 3,000 meters or 3 kilometers, 3 km. And so let's see, for the walker, we've got 3 kilometers divided by 4 kilometers per 1 hour. It's going to be what? 0.75 hours. Now for this guy, it's going to be half of it is going to be 1.5 kilometers, and he's got what was it, 2.8? So 6.8 kilometers per hour this way, plus the other way is 1.5 kilometers, plus 4 minus 1.2 kilometers per hour. And he's going to be 1.47 hours. So he takes longer than the walker. Interesting. All right. Number 43 says a test rocket starting from a rest at point A is launched by accelerating it along a 200-meter incline of 1.9 meters per second squared. The incline rises at 35 degrees above the horizontal, and the instant the rocket leaves, its engine turns off and the rocket is subject to gravity only. Ignore air resistance. A, find the maximum height above the ground that the rocket reaches, and B, the rocket's greatest horizontal range beyond point A. So we have something like this. This is 35 degrees. And this is 2,000 meters, 200 meters. Okay, and we want to know how high it reaches and the greatest range. So I want to know this B here, B there. So I've got, it starts from rest, right? So I know that, let's see, I've got an acceleration of what? 1.9 meters per second squared, 1.9 meters per second squared. So I need to know my velocity here. So V final squared equals V initial squared plus 2A delta X. So this is 0. So V final squared equals 2 times 1.9 meters per second squared times delta X is, let's see, what is it? 200.0 meters. All right, so I'm going to take this square root of both sides. And I'm going to get, let's see if they solve it for me. Okay, it's going to be 27.57 meters per second. So this is going to be 27.57 meters per second. All right. Now, I need to know my X and Y components. So let's go ahead and do that now. Let me get my board space. Okay, let's see. And I need to know this height here also, but we'll do that in a minute. All right. So I want to know, let's see. V sub X and V sub Y. All right. V sub X at that point equals 27.57 meters per second times cos 35. And that's going to be 22.57 meters per second. And V sub Y, V naught Y, V naught X is V naught Y is going to be that same value, 27.57 meters per second times sine 35. And that's going to give me 15.81 meters per second. All right. Now, am I asked for how much above that, or what am I asked for here? Let's see. Find the maximum height above the ground that the rocket reaches. So I need to know this height. So let's see. This is going to be my Y value. So sine 35 equals Y over 200 meters. So sine 35 times 200. Let's see if they've solved that for me. Let's see. I don't know. I'll just solve it on my calculator. On clear. Sine 35 times 200. That's going to be 114.71. This is 114.71. All right, so let's go ahead and do this. So we need to know when this guy is 0, this guy is 0. So here we go. We've got V final equals V initial plus acceleration times time. Did I want to do that? No, I'll do it a different way. No, let me just do this. I'll go ahead and use that I'll just do it as V final squared equals V initial squared plus 2A delta X. So I'm going to have 0, because I know that equals 15.81 meters per second quantity squared plus 2 times negative 9.8 meters per second squared times delta x. So I'm going to have, move that over. Let me give myself some board space. Let's see. I've got 15.81 meters per second. That's going to be squared, and I'm going to subtract it for both sides. Divided by 2 times negative 9.8 meters per second squared equals delta x. And let me go ahead and do that. On clear, 15.81 squared equals divided by 2 times 9.8. And that's going to be 1275. So add that to that, plus 114.71 equals, I get 127.46. So my height, Y max above ground is 127.46 meters. All right, that's Y max. All right, and the solution say 128. Okay, well, I must have have something from rounding. So 128, I got 127.46. All right, now I need to know my time. All right, so in order to solve, let me get myself some board space. All right, my time, and I'm going to keep these components there. All right, I guess I'll use the quadratic formula. There's an easier way to do it. I'm going to go ahead and use this value here, Y max, and just determine how long it takes something to fall from that value. I could use the quadratic, I could use set up, let's see. There's many ways to solve this. I could set up Y equal to a negative 114.71 and use a quadratic formula, but I don't want to go through all those changes. So let me just determine how long it takes an object to fall from this height, and I'll solve for t. Oh, wait, is that my best? I got to get my total t. Now I'm going to have to do the quadratic formula. Let's see. How did the solutions do it? Let me just go ahead and do what they did. They did the time of the area vertical component. Yeah, they did it that way. All right, so let's go ahead and do that. I'm going to call that my 0th position, 0, 0. I'm going to get a negative 114.71 meters. This is going to be x final equals x initial plus v naught t plus 1/2 at squared equals 0, because I'm calling that initial 0, plus v naught is 15.81 meters per second times t minus, this is getting to be too crowded. Let me just go ahead and get all these little things out of my way. All right, okay, so I'm going to use that y component. So once again, it's negative 114.71 meters. It's going to go, right, and that's that, equals 0 plus v naught in the y direction is 15.81 meters per second times t minus 1/2 times 9.8 meters per second squared times t squared. And going ahead and doing that quadratic formula and using the quadratic formula solver, I'm going to go ahead and snag their solution from the solution manual. The t is 6.713 seconds. So I'm going to go ahead and assume they're right. T equals 6.713 seconds. And then going ahead with this, figuring out how far from what the launch. Okay, so the rocket's greatest horizontal range beyond point A, so beyond here. All right, so what I'm gonna do is X final equals X initial plus V naught T plus 1/2 AT squared. So I need this guy. So I need to know my point here. So X equals 200 meters times cos 35. So what is that? On clear. Cos 35 times 200 equals 163. So X final equals 163 meters plus V naught is going to be 22.7 meters per second times T is 6.713 seconds. And then we don't have an acceleration in that direction. And so I'm going to go ahead and snag their solution here. It's going to be 315 meters. So X range, they call that range, is 315 meters. All right, very good. That was number 43. All right, 51 says, a toy rocket is launched with an initial velocity of 12 meters per second in the horizontal direction from the roof of a 30-meter tall building. The rocket's engine produces a horizontal acceleration of 1.6 meters per second squared times t in that same direction as the initial velocity. But in the vertical direction, the acceleration is g downward. Ignore air resistance. What horizontal distance does the rocket travel before reaching the ground? Okay. Okay, so I'm asked to find the range. All right, so let's see. The rocket is launched with an initial velocity of 12 meters per second in the horizontal direction from the roof of a 30-meter tall building. So what I need to do here is find out how long it's going to take to fall. Okay, so let's see. We got 30 meters. So at 30 meters, I'm going to use that y component. There's no initial velocity in that y direction. 30 meters equals x. I'm sorry. Let me just do it properly. Okay. So using that y component, we want to know it's going to be, we're going to call that ground zero equals 30 meters plus V naught T plus 1/2 GT squared. All right, I know it has no initial component in that direction. It's launched horizontally. So negative 30 meters equals 1/2 times negative 9.8 meters per second squared times T squared. So negative 30 meters times 2 divided by negative 9.8 meters per second squared under the radical is going to equal to T, right? Multiplied by, just did the algebra. And T is going to be 2.47 seconds. 2.47 seconds. All right, that's T. That's how long it's in flight, because that's how long it takes to drop. All right, let's go ahead and finish the rest of this. Now we were given a acceleration value. Let's see, what are we given here? We're given all right, where you're given an initial velocity and we're given an acceleration. All right, but the acceleration, all right. Let's see, we are the initial launch and the horizontal direction from a roof an acceleration of 1.6 meters per second cubed times t in that same direction. All right, so we have t, now we've got, we need v sub x is going to equal to v naught sub x plus the integral from 0 to t of a sub x times t dt. And that's going to equal, v naught is 12 meters per second plus, and what did we have, 1.6? 1.6 meters per second cubed, 1.6 meters per second cubed times t. That was a sub x. Okay, so we're going to take the integral there, and we're going to get 0.8 meters per second cubed times t squared. And then we just fill in the value for t, which is 2.66, wait, what is t? 2.43, 12 meters per second. And we want to know x direction, right? All right, so we have to integrate one time to get that velocity. This is going to be 12 meters per second, and plus the integral of that, which is 0.8 meters per second cubed times t squared. Now we have to integrate the whole thing again to get the position. So x equals 12 meters per second times t plus, what would that be? 0.8 is times 3 is, let's see. All right, in integrating this, that would be 0.8 meters per second cubed divided by 3 times t cubed. And that's going to be, let's see, x equals 12 meters per second times t plus, I don't know what that is, 0.8 divided by 3 is 2.266. All right, 0.2667 meters per second cubed times t cubed. And this is going to be, if you put in t equals 2.4 seconds. All right, so from, let me just do it proper. 0 to 2.4. Need a little more board space. 2.474 seconds. The final value is going to be 33.7 meters. Okay. All right, so you had to integrate twice here, once to get that velocity from the acceleration and once to get that distance from the velocity. All right, and that's it for chapter 3.